Let's now move on to quantitative data summaries. You should be able to make a frequency table, a histogram, a frequency polygon, an ogive, and a stem and leaf plot. For the first example, we're going to create a frequency table for data collected on the number of siblings of students in a particular class. As you can see, I've already taken the raw data and organized it according to its frequency. Remember, frequency is the number of times the data point shows up. So number of times it shows up. So in this particular class of students, there was 1 student with no siblings, 11 students with 1 sibling, 5 students with 2 siblings, 1 student with 3, so on and so forth. And notice, even though there were no students with 4 siblings, I still put that in the table here because these are not qualitative values here. They are quantitative, so I don't want to skip over any. So I started at 0, went all the way up to 1 student had 8 siblings. So, as seen in a previous screencast, this Greek letter sigma it acts as a sum in mathematics. So this is saying add the frequencies since f is the frequency. So if you add these frequencies up, we get a total of 20. So 20 students were surveyed. And then relative frequency is the percent of the whole. So 1 student out of 20 had no siblings. 1 student out of 20 is 5%. 11 students out of 20 had 1 sibling. That's a total of 55%. 11/20ths is 55%. 5 students out of 20 had 2 siblings. 5/20ths is 25%. Let's complete the rest of the table for relative frequency. And of course, this down here, sigma RF, means add up the relative frequencies. And if we add these all up, we get 100%. Now we have a new concept that was not part of the qualitative data. In fact, it doesn't even make sense with qualitative data. With frequency, you can find the frequency for qualitative or quantitative data. For relative frequency, you can do that for quantitative or qualitative data. But cumulative frequency only makes sense with quantitative data, and you'll see why as I define it. Cumulative frequency for a particular class is that class's frequency plus the previous frequencies. So the reason this doesn't make sense, well, actually first let's do it and then I'll explain why it doesn't make sense with qualitative data. So for this first class of no siblings, there was a frequency of 1. So there's nothing before that class, so the cumulative frequency is 1. Then for the second class, for having 1 sibling, there were 11 students or 11 people, a frequency of 11, plus you want to add to that the previous ones for 0 students. 11 plus 1 gives us a cumulative frequency of 12. Then for this third class, where the number of siblings is 2, that frequency is 5, but you want to add to that the previous 2. 5 plus 11 plus 1 gives us a total of 17. Or if you want to think about this differently, 1 plus this 11 gives me that 12. 12 plus the 5 gives me this 17. 17 plus 1 gives me this 18. 18 plus 0 gives me 18. 18 plus 1 gives me 19. 19 plus 0 is 19. 19 plus 0 again is 19. And 19 plus 1 is 20. Please notice that the cumulative frequency of the final class is the same thing as sigma f. Those should be the same always. Now, the reason this only makes sense with quantitative data, meaning you can't find the cumulative frequency of qualitative data, is because of this. Again, the cumulative frequency is the class's frequency plus the previous frequencies. The idea of previous implies some sort of order. There's an order relation on the set of numbers, 0, 1, 2, 3, 4. For example, 4 is greater than 3, or 6 is greater than 1, or 3 is less than 8. there's an order relation on the set of real numbers. Whereas if this was qualitative data, say Ford, Chevy, Hyundai, there's no such thing as Ford is less than Chevy or greater than Hyundai. Something like that doesn't make any sense. So because of the required order relation, cumulative frequency only makes sense with quantitative data, not with qualitative data. Now, before we move on, we've completed our frequency table here. I want to make sure you understand the meaning of a number like this. So what does that 19 right there mean? A cumulative frequency of 19 for the class that has 5 siblings associated with it. Well, remember, this 19 came from adding all these previous numbers together. So this 19 represents 19 of the students in this class have 5 siblings or less. That's the previous part. So 19 students have 5 siblings or less. So you can see cumulative frequency has meaning. And you'll also see that the graph that goes with the frequency, with cumulative frequency, is what we call an ogive, which is coming up in a future screencast. Let's first focus on creating the bar graph for quantitative data. A bar graph for quantitative data is called a histogram. With qualitative data, the bar graph is called a Pareto chart. For quantitative data, it's called a histogram. Let's take a look. As mentioned, a bar graph for quantitative data is called a histogram. Now, there are a couple of different rules with a histogram as compared to a Pareto chart. With a histogram, the bars must touch for consecutive non-zero frequency classes. You'll see what I mean with that in a minute. But the bars do touch with a histogram, whereas they don't with a Pareto graph. With number 2, you have no control over the order of the bars. With the Pareto graph, we specifically put the highest frequency data to the lowest frequency data, so the bars went from tallest to shortest. You have no control over that here because of the order relation on the set of numbers. And then also, just like with a Pareto graph, bars are all the same width. So let's take a look at this. Histogram, you can also do either frequency or relative frequency on the vertical axis. If you're not told to do one over the other, I highly suggest frequency. It's just simpler, so you don't have to deal with the decimals. In general, I don't specify. You can do whichever you'd like. So our frequencies, we go from 0 all the way up to 11. So that's not too bad. Let's count up by 1. So you got 0, of course, there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Of course, when you guys do this stuff on quizzes or exams, there will be grid paper, so it'll look nice and neat. Now, on the horizontal, we have our number of siblings. And the number of siblings in this data ranges from 0 to 8. Now, technically, 0 is right here, but because we're going to put bars around those numbers, I don't really want to write over here on this side, so I'm just going to offset this for the time being and put 0 here. And then, of course, we're going to count by ones. 3, 4, 5, 6, 7, 8. And now I can put in my bars meeting the specific frequencies. So the number of students with 0 siblings was 1. So for the 0 bar, I need to go up to a height of 1. Now notice I need to go halfway between the 0 and the 1 here because the bars need to touch. So there's my first bar. And then the number of students with 1 sibling was 11. So this next bar needs to go all the way to a height of 11 and come down halfway between the 1 and the 2. Again, you don't have to color these in, it's up to you. The next bar for 2 siblings has a height of 5. The next bar has a height of 1 for 3 siblings. Then for 4, there was none. You can put a line here if you want, or you could just leave it blank. Either is fine. 5 siblings, there was 1 student with that scenario. Then 0 had 6 siblings, 0 had 7 siblings, and then 1 had 8 siblings. So we've got that. So aside from these couple of spots right here, where the frequency of that class was 0, notice that the bars actually touch. So that's a big difference with histograms. The bars must touch, and you have no control over the order of the bars. Notice it grows here, then declines, and then grows again briefly, declines, and grows again. So you have no control over the order of the bars. And as you can see, by far the most common in this particular class of students was having one sibling.